So let's look at this term a little more carefully. We get some quadratic expression P and Q vanishes. So this term we can write as integral A U A E Q, where A is a Lie algebra index, and mu is the moment map. So it's some bilinear map from V and V star to the Lie algebra. So if we vary A, we find that U A E Q is equal to 0 for all A. But so I hope this is a familiar equation. The vanishing of the moment map, but this is always what one finds with the phase space of the gauge theory. But now we have to divide out by the gauge symmetries. So we can always set A equals 0 by some gauge transformation, so working on the real line. And then we're left with constant gauge transformations. Which are just elements of this group. So what we find is that the solutions of the equations of motion modulo gauge is given by the zero locus of the moment map modulo G. So we're set with like set of P, Q, where it's equal to 0 modulo G. So this is called the symplectic reduction. Any questions about this?
I'm assuming Hamiltonian is 0.
Yes. Well, nothing would change if we had nothing essential would change if there was a non-zero Hamiltonian. You would so if there was a non-zero Hamiltonian, we would have a term. I would add on some G invariant function. And then if I solve the equations of motion, I would find that they would not be covariant constant, but they would satisfy some differential equation, first order differential equation, which tells me that they're determined by their value at t equals 0. And at t equals 0 would be some element here. So the space of solutions to the equations of motion would be the same, but now this space would have a non-trivial time evolution given by a Hamiltonian on the symplectic reduction. So what I want to explain now is how to, we want to put this into BV formalism, like what will change if we write down the space of local operators, which would be functions on solutions to the equations of motion. And if we calculate it, what we'll find is that the Hamiltonian version of the BV formalism, which is sometimes called BFV, but I feel there's too many letters hanging around anyway. So this is something useful to know because, if you read textbooks, they'll sometimes present it in the Hamiltonian formalism, or in the vertex algebra setting, it's often written in more Hamiltonian way. So to do this, we need to introduce antifields and ghosts. So the antifields for P will be called, say, P star, Q star. These are fermionic. Also A star, fermionic. The ghost. Let's think about a little bit about what dimension these fields are. So everything is in diffeomorphism invariant on the real line. So we want this diffeomorphism invariance to still be present when I introduce these fields, and I want the BV anti-bracket to be diffeomorphism invariant. So the BV anti-bracket is going to be, or the symplectic pairing will involve pairing P with P star. Since P is a zero form, P star, Q star will be one forms. Similarly, A star will be a zero form. Chi, ghosts are always zero forms, and chi star will be a one form. So we have this nice feature that all of the fields arrange into several copies of the de Rham copies. So I have here's ghost number 0. Ghost number 1, I'm going to have omega 1 for B. This field is called P. This field here will be Q star. So the reason that this is the dual to this guy is because you want the transforms in the dual representation of the gauge group. So there's a natural pairing between this and this. And I also have the antifield to A. And then the antifield to the ghost. Okay? Any questions? Now, on this big space, it's often useful to write down that the linearized BV operator. So this is the operator whose kernel over here will give you the linearized equations of motion, and whose image this way will give you the linearized gauge transformations. So the linearized equations of motion just say BP is 0, and the linearized gauge transformations just say A changes by D of the gauge transformation. And we also to make this compatible with the symplectic pairing, we have to have a term up here. So then the fields with a linearized BRST operator just look like a bunch of copies of the around. Okay, so now we've written down the fields. The next step is to figure out, like, what are the operators? And this is the point at which the notation becomes very confusing, because traditionally it's hard to distinguish between the field A and the operator which evaluates the gauge field at that point. But here it's kind of important to make that distinction.
What does it mean to evaluate a gauge field at a point?
It's a one form. I take its value at a point is in the cotangent space at that point.
But it's only up to gauge.
No, it's literally a one form. And because because we're going to write down a cochain complex, so that won't be a closed operator.
I see. Okay.
So what are the operators? So my terminology is going to be a little bit confusing. I think it may be slightly contradictory. So I'll use this for the Why don't I have an idea? So I'll use a subscript operator with some subscript integrate. Kind of is. So there's position, which sends e of 0, and also I can take some derivatives of that. Operator, this momentum position, q to q of 0, and its derivatives. Similarly, Q star, O Q star, OA, OA star, O chi, O chi star. So these are of ghost number here -1, -1, 0, -1, 1, -2. Because it's the reverse of what the plus means. Now, next we're going to figure out what's the differential operators. This will have two terms. We'll have a linear term, which comes from the kinetic term in the action. And the linearized gauge transformations, and then a nonlinear term. So let's just figure out the linear term first, because we can just read it off this complex. So I'll call it Q linear. So we just look at this complex, and our operators are linear functionals, so the differential just goes the other way. The operator, which is a function of A, goes to the derivative of the operator, which is a function ghost. Okay. Any questions about that? So what's this saying? We're just like, the gauge field varies by the derivative of the gauge transformation, and the equations, like the image of this here is going to impose the equations of motion, which says that this is constant. This is constant too. Now, if we take the cohomology of this, what do we find? We can't build any gauge invariant operators from this guy. Evaluating the gauge field or any of its derivatives, that's never going to be gauge invariant because I'm always going to get something here. But I can build a gauge invariant operator. This guy. That's right. So, cohomology things that survive here with this thing Q, OP, and OA star. But not their derivatives. Here, like the derivative of this guy, that's 0 by the equations of motions. That's not an operator we're going to see. Here, well, this is the ghost. So why would the derivative of the ghost not be in the algebra? That's because one way to see it is this equation. It arises as the variation of some gauge. Or another more geometric way to say it is it's a gauge transformation which does not preserve the trivial field A equals 0. Now, if you're being a bit more mathematical, you could have said, we just look up here on the top blackboard and realize we could have gotten this answer by taking the Ram cohomology in every line and just looking at its dual. The Ram cohomology here picks up something in degree 0, and it picks up two things in degree 0 there, and it picks up this thing in degree 0 here. So the usual terminology for these operators is, this is normally called C, and this guy is normally called B. And that's just, these guys are normally called P. So that once we take the cohomology with respect to this term, the algebra of operators we find are just polynomials in these variables. So, okay. Now, I've only written down the linear term, so what's the nonlinear term? So if you remember, the nonlinear term could be kind of complicated, but it was best understood by thinking about the BV Lagrangian. At a cubic term, interval P, A, q plus p star chi. This tells us that p transforms under this gauge group, plus q star chi plus chi star. So and did I get everything? Plus a star chi.
Can you say one more time how you wrote that down?
Okay, so here's the term I originally had. So here I'd say, well, this field transforms under the gauge symmetry. So anytime a field transforms under the gauge symmetry, in the abstract way to say it is the field and its antifield form a shifted symplectic vector space. So there's a shifted moment map. And I multiply that shifted moment map by the ghost to get this term. And that's something that tells me how it transforms, because if I take BV bracket with it, I'll find the transformations of this field. And that tells me all of these terms. This last term, it's something related to the Chevalier-Allenberg differential.
So that's the one-dimensional version of something, the structure constants, C, A, C, B.
Yes.
Exactly.
Yeah. So, like, if you take the BV anti-bracket with this guy, it gives you something which takes an operator to a new operator. Like, what does it do? Well, suppose I stick in this guy, it's a star term. Well, that must pair with an A, which only appears there. So, for example, S cubic O A star, I'm going to pick up the moment map, because this term here is the moment map, plus a term which isn't going to matter. So this term doesn't matter. So it doesn't matter. As these operators are not in the cohomology. Okay, so now since this guy was also known as B, we find that there's a term, like the differential, the nonlinear term in the differential, I'll call Qn sub L of B, is the moment map. So what this term is doing is we're introducing an operator, fermionic operator called B, whose differential is the moment map. So we're imposing the moment map equation homologically by using its Cauchy complex. But this is good because sometimes the moment map equation can be kind of degenerate, and it's important to do this. So in a similar way, you can look at each of these terms and figure out what it will do to the operators. And I hope that kind of constantly fluctuating notation is not too confusing. So if you look at the second term, B star chi, This gives us a term, the nonlinear term of P, because the antifield P star contracts with P, will be P times the ghost. Similarly, and the other interesting term is chi star, because this guy pairs with chi, I'll get a term where the ghost becomes the square of the ghost. So let me kind of write it out again one more time just to be sure. This is like in general the Hamiltonian form of the BB complex. Which we've derived from a Lagrangian one. So we might start with M, symplectic manifold, possibly infinite dimensional, G, which acts on M by Hamiltonian vector fields. Then we consider functions on M tensored the exterior algebra of G star, tensored the exterior algebra of G, where the generators here are denoted by C and B. And the differential is d of q of BA is equal to the moment map. Q of a function is equal to ghost times the way this function transforms under the gauge symmetry. That's a good notation for that. So this means the infinitesimal translation of this function under my actual symmetry. And Q of CA is half F A B C C C.
So this is all assuming that the Hamiltonian is zero, or
no? This is always the case.
okay.
So I'm writing down the algebra of operators, and the Hamiltonian is an element of that.
Right.
So
Some N.
yeah, there'll be some like H in this algebra. So you might start with a gauge invariant Hamiltonian, and then you so it's some thing on this manifold, it's just that. But if you had in more complicated situations, you might have to, it might only be gauge invariant on shell or something, and then you might have to add on other terms. So yeah, if you work hard, you can in principle derive the Hamiltonian formulation of Yang-Mills theory, for instance. In that case, M will be the cotangent bundle to the space of one forms on space. And the gauge symmetry will be the infinite-dimensional group of gauge transformations just on space. And then the Hamiltonian will be given by Q squared.
Yeah. The moment one would be the Gauss's law.
Yeah, so let me write it like so. So in that case, M is the cotangent bundle of the space of one forms on your three-manifold X. So I'll call something in the base, I'll call A, and something in the fiber, I'll call B. And this cotangent bundle direction really represents the first normal derivative field. So D is the space gauge transformations on space. And this acts in the natural way. And then the Hamiltonian so one derives the Hamiltonian by thinking about the Yang-Mills equation. So this describes the space of germs of solutions of the Yang-Mills equation. To specify a solution of the Yang-Mills equation, I need to specify its boundary value and its first normal derivative because it's a second-order equation. Then I evolve it in time. I give some flow in this manifold. That flow is Hamiltonian. What's the Hamiltonian function? You can calculate it, but I think it just looks like base b squared. Okay, so let's do another example in this vein. So let's see what happens when we work with two-dimensional chiral theories with gauge symmetry. And we're going to recover this construction from the theory of vertex algebras, which is called the BRST reduction. Okay, almost exactly the same. Suppose I have some fermions. And I have this Lagrangian. So this is the theory of some number of complex fermions on the plane. Chiral complex fermions. So to gauge it, we introduce A. I assume my gauge group is GLN. Now, there's something a bit, to physicists might seem a little funny, that I don't have a full gauge field. I only have the 0, 1 component. But this turns out to be the correct thing to do. The reason being, what do I need? What kind of a bundle do I need to talk about a system of fermions living in that bundle? Well, because I only have the d-bar operator here, I only need a holomorphic bundle. So the natural thing to insert if I want to have covariant derivatives is just a 0, 1 gauge field. And then, as before, I just write down this Lagrangian. So notice that as in quantum mechanics, there is no kinetic term for the gauge field. So this might appear confusing at first, until you realize that because this gauge field only has one component, locally it can be always set to 0 by a gauge transformation. It locally looks like some function times dz bar. Then that function is d by dz bar of something. That's something I can figure out by integrating. So this is a perfectly fine action functional, even without a kinetic term. Now let's calculate what are the algebra of operators. So the analysis goes almost identical to the case of quantum mechanics. So I'll do it a bit more quickly. So first you realize that there are no z bar derivatives appearing in the algebra of operators. That's because the equations of motion tell us that, the linearized equations of motion tell us that these guys are holomorphic, so they're independent of z bar. And the gauge transformations which preserve A equals 0 are those which have no z bar component, because A, under infinitesimal gauge transformations, A transforms as d bar chi plus chi A. So if I linearize the problem, I find that the gauge transformations which preserve the A equals 0 have chi, which does not have a z bar component. So the operators are psi I plus their z derivatives and the C ghost, which is the function of the parameter of the gauge transformation chi, plus its z derivatives. And also the B ghost, which is a function of the anti-field to the gauge field. And also in C. So it's exactly like quantum mechanics, except that now we have this extra direction. So everything propagates. If we were in Lorentzian signature, we could have said, well, Lorentzian signature z and z bar become two null directions. In the z direction, nothing is happening. In the z bar direction, it's just the same as we had before. So it looks exactly like quantum mechanics, except everything is now a function of z. Now, what's the BRST operator? So it commutes with formation of derivatives. So I only need to tell you what it does on things with no derivatives, and it has the same form as before. So this operator psi I psi j is also called a current. It's the current which generates the Cas-Moody action, this chiral theory with UN symmetry. So this is the standard. You read a textbook, string theory textbook or textbook in vertex algebras, they will tell you about the BRST reduction and say, oh, they will tell you that we did this procedure where we take our original algebra of operators and adjoin these new operators B and C with this differential. So the reason I wanted to explain it is I wanted to point, this really is an example of a super general procedure that works in any gauge theory. Just applying it. Any other questions? So I hope some of you guys have seen this construction before, right? Drinfeld's papers or something. Maybe. Oh yeah, one more point. So people will often say that instead of writing this operator, they will say it comes from the BRST current. And that current is the integral, contour-integral, of C psi psi plus C B. So this comment is something that's only going to be familiar to understandable to people who know about this language of vertex operators. So there's some standard procedure to say, if I have a current like this, it acts on the space of local operators. And the way it acts is by B contracts with C, psi contracts with psi I contracts with psi lower contracts with psi upper. And if you do that contraction, you find this operator. But this BRST current should be familiar to you guys. It's nothing but, it is like the same thing as the cubic term in the BV actual function. Psi star plus so it's almost the same, except I have some anti-fields appearing. And the reason they're not exactly the same is they're related by what's called descent. So if I integrate this over a disk, so the failure of this to be invariant under the linearized guy, this is the boundary terms.
Is it also that people usually use that in the string theory context, are always big OPEs, and then here the procedure is to use the BB bracket to
yes.
I guess it's kind of the same, at least in the case of Fermionic fields, because the OPEs only have the simple poles. So
yes.
It's kind of like just using.
Yeah, absolutely. So like for fermionic fields, like the BB bracket involves a delta function, and the OPEs involve a 1 over z.
Right.
And d bar of 1 over z is a delta function. So they're kind of related in the double complex. So that's what this descent procedure is doing. So there's some formal way, say, here this is some Lagrangian of degree 1. Sorry, this is a Lagrangian of degree 0, and I can relate it to a current of degree 1. Just like, it's really Noether's theorem. Yeah, it'll be slightly off topic. So if M is -1 symplectic, and I have some symmetry, then I get some function h rho, where h of rho bracketed with the function, any other guy. So if this is a symmetry of degree 0, then what kind of thing must this guy be? Well, this bracket is of degree 1. So therefore, for the degrees to work out, this must be a function of degree -1. For example, if M is a cotangent bundle of some vector space, and I have P star, well, what's the usual formula for the Hamiltonian thing associated to some symmetry? I just take my P and my Q and I multiply them. Here I do the same thing. If I have some symmetry where rho of Pi is some matrix, J, then the Hamiltonian is Mi Ej E star I. So because this is an antifield, this is some non-zero degree, so it would be -1. So this is completely trivial. It's far more trivial than Noether's theorem. So the original Noether's theorem is the same thing, but done on space. If we work on space, the symplectic pairing is of degree 0, and it should do the same thing. So what's the relationship between them? There's some kind of general descent. So Lagrangians of degree 0, of degree, say, A, are equal to currents of degree A plus 1. So if I have a symmetry, it gives me a Lagrangian of degree -1, it's a current of degree 0. If I have an ordinary Lagrangian, it's of degree 0, so I get a current of degree 1. So we've spent a lot of time on homological stuff, but I feel this is it was pretty tricky. So, any questions about this? It's not obvious that it's true. It's something about some calculation which leads to it. Maybe I'll do it next time. Let's see. So what I'd like to start doing next is to integrate the two things we've understood. So we've understood the BV formalism, and we've understood effective field theory. Now we got to put them together. So we'll start doing that next time by trying to understand the quantum master equation for an actual quantum field theory, and we'll realize how it has to be renormalized. And that will link us back with the renormalization group flow. So we will do that next week, and next week we'll kind of have the example we'll use a lot the example of Chern-Simons theory in dimension 3 because that's a very simple example to play with in this setting. Young-Mills theory gets a bit technical. Simon's theory is nice. Okay. So we'll stop there.